Hello, guys. So this is going to be the seventh installment of the show's algorithm. It is assumed that you have already covered um, the first up to the sixth lesson, and from there, in the previous lessons, we already discussed the theoretical basis of Shor's algorithm and how to encrypt and decrypt and how to crack the Shor's algorithm using the period finding. And there we also discussed how to create the quantum Fourier transform. So in this last session, we're going to connect all of the concepts and show you the entire Shor's algorithm. Okay, so let's begin. Okay, hello again. So let's now start with session 7, programming the Shor's algorithm in Qiskit. Okay, so the previous lecture we showed the theoretical foundations of RSA, and we learned how to decrypt using a public key and private key. And then we also learned how we can crack the RSA using a method known as period finding, assuming that you're able to compute for the period. So, to make things a little bit more self-contained, what we'll do now is to give a review of the theory of RSA very quickly. So, according to this theory, you have a prime numbers, large prime numbers P and Q, which when you multiply will give you composite number letter N. And then we then choose a number E, which is what we'll use in order to encrypt messages. So the number E has a property in such that it doesn't have any common factors with P minus 1 and Q minus 1. Okay, and then the set of numbers N, E, is called the public key. Okay, next. So given a message M, we want to encrypt this using RSA. So what we'll do is we are going to raise this to the power E and get the remainder when we divide it by the number N. So this is the formula. The ciphertext C is equal to M raised to the E, modulo N. Okay, so N is just the remainder. Okay, now the public knows N, E, and C. Okay, and what we want to do is to decrypt the message using a quantum computer through a process known as a period finding. Now, the period is the number R, which is defined using this formula. So you know that R is a period if, given the ciphertext C, you raise it to the power R and get the remainder when dividing it by N. And if you get the number 1, then R is the period. Okay. So now what can we do once we have found the period? Once we have found the period, what we can do is compute for the modular inverse of modular inverse of E with respect to the modulus R. And that modular inverse, we call it D prime. Okay. So given this formula, we want to find D prime such that E times D prime modulo R, which is the period, will give you 1. Okay. And by the definition of modular arithmetic, we know that if this is true, then we know that E D prime is equal to some number S, positive number S multiplied by R plus 1. Okay. So we don't really care what that number S is, but we just know that if E D prime mod R is equal to 1, then there is a number S such that S times R plus 1 is equal to E D prime. Okay, definition of modulus. So once we get D prime, what can we do with it? So what we can do is, given the ciphertext C, we can raise it to the power D prime, which will eventually give us the ciphertext. And this is the mathematics of it. Okay, so C raised to the D prime will give you ME raised to the D prime. Okay, so ME is nothing but the definition of C. Okay. Now, so MED prime will then give you, but we know that ED prime here is equal to this one here. Okay, so that's equal to M raised to the S dot R plus 1. Okay, so M raised to the 1 will give you M, and then M raised to the R is this one here. But since R is a period, we know that this is equal to 1. Okay, so therefore C raised to the D prime is nothing but your decrypted ciphertext. Okay, it's your plain text. Okay, so let's have an example. So let's have numbers P equal to 3, Q equal to 5, and let's choose E so that E does not have anything in common with P minus 1 and Q minus 1. Okay, so let's choose E to be equal to 3. Now, if our message M is equal to 7, then we can encrypt 7 by using this formula. Okay, so 7 raised to the 3 modulo 15 is nothing but 13. Okay, so this is our encrypted text. So given only the knowledge of C equals to 13, E equals to 3, and N equal to 15, we want to find the original message M. Okay, so let's give an overview of Shor's algorithm. Shor's algorithm requires 2 registers. Okay, the input register and the output register. Okay, let's so let the input register represent all numbers, okay, between all numbers X between 0 to 2 to the n minus 1, okay, where n is the number of qubits. And then the output register, let me just erase this because initially this one is equal to 0, okay, the input register. And then we have the output register, okay, so we have the input and then the output. Now, so the input will represent the number X, and the output will contain the result of this function here. okay, to contain f of x. Okay, sorry. Okay, next is we do this. So the Shor's algorithm involves the following. It will first, we know that we have the input and output register, which are both initialized to 0. And then what we want to do now is to apply the Hadamard transform into the first into the input register. So we have H here, and apply it to the n qubits in the input register. Okay. So this one will give us 1 over the square root of 2 to the n, summation of x equal to 0, 2 to the n minus 1, and this will become x here. Okay. And this is the tensor product of the output register. So once we have that, the next thing we'll do is to apply the modular exponentiation function. So we have a so here what we'll do is we apply an operator which will compute for the f of x. Okay, so u f of x apply to everything here. Okay, and it will result to 1 over square root of 2 to the n, summation x equals 0, 2 to the n minus 1. X will stay the same, but then 0 will then become c to the x modulo n, okay, which is nothing but this one here. Okay, now after doing that, after putting the input and output register into this superposition, the next thing we'll do is we want to measure the output register. Okay, so when you measure the output register, it will give you a number. Okay, and that number will then, so when you measure the output register, it will give you a certain number, and then it will collapse the input register into a superposition of those states whose modular exponentiation value is equal to the number that we have just measured. Okay, so there are assume that there are m of these m of these states. Okay, so let me just explain that further. Okay, let's go to this one here. Okay, so I prepared this for you. Okay, so this one I'm using the application called R, so I'm very familiar with it. So assuming that you have a you have 13 as your base number. So first we want to raise 13 into this okay, first we generate 0 to for example 16. Okay, and then we raise 13, the number 13, raise it to 0 to 16. Okay, okay, so actually it works. So let me just define this, and then 13 raised to the n. raised to the n, give you, and then I'll get the, so this one is, so here we assume that C is equal to 13, and then we want to raise 13 to all possible values of the input register. Okay, sorry, the input, all possible values input register is actually 0 to 15. So 13 raised to the n, and then we'll get the modular exponentiation, assuming that we have, so we have 15 as the base. Okay, so we have, so this will give you 113 for 7. You can see it's repeating. Okay, so it's periodic. Now, this will become the value of your output register. Okay, so the input register looks like this, and the output register looks like this. Okay, now when you measure the output register, it will give you a certain number. Okay, so let's say that when you measure the output register, it gave you the number 4. Okay, so the number 4 is therefore, the number 4 is corresponds to numbers in the input register, and these numbers are 2, okay, 6, 10, and 14. Okay, so when you measure the output register, it will give you a number, for example 4, and by measuring the output register, it will collapse the input register into a superposition of those numbers whose value of the function f of x gives you 4, and these are 2, okay, these are 6, and these are 10 and 14. Okay, so if we go back here, let me show you again. So these are your, this thing corresponds to your numbers in the input register, because we have measured the output register to be f of x0. Okay, so these are the corresponding states. So once your input register is in this superposition, the next thing you do is to apply the quantum Fourier transform, okay, to the input register. Now the Fourier transform is defined to be this one here. Okay, so given an x, a basis vector, okay, so one of those numbers in the input register, if you apply the Fourier transform, it will give you this formula. So this will become 1 over square root of 2 to the n multiplied by e raised to the 2 pi I xy. Okay, so x corresponds to this, y corresponds to this, over 2 to the n. So if you apply it to the input register, this is what will happen. Because of the linearity of the transformation, you can apply it to each term of the sum. Okay, so what will happen is you apply it to here. Okay, now applying the Fourier transform to x0 plus kr, this is what you will get. Okay, you can actually factor out this thing here. Okay, so what will happen is that this becomes the probability amplitude. Okay, And this one is the summation of y equals 0 to 2 to the n minus 1. And this is your uh, um, vector y. Okay, and this is the probability amplitude. So once you have that, you then measure the value of y. So when you measure the value of y, you will then get a there's a high probability that the value you get is an integer. Okay, so we discussed this in one of the previous lectures. But so the value of y, once you get whatever is the value of y that you get, you just have to compute the continued fraction expansion of y over 2 to the n. And then eventually you will get a fraction j over r, okay, which will appear as one of the partial sums of the continued fraction expansion. Okay, so we covered this continued fraction expansion in one of the lectures. You can go back to that lecture and review it. And then once you have computed for the period r, you can then verify first that it is a period, okay, by raising the ciphertext c to the value of r modulo 15 to get, and if it's 1, then you have found your period. And then you compute the inverse modulo of e, okay, using this formula. So once you get d prime, you can then use d prime to compute for the plain text. Okay, so this is now your plain text. Okay, so that's as far as the theory. The next in the next section, we are now going to use Qiskit. We're gonna show how we implement all of this in Qiskit.